Chapter we are looking properties of eigenvalues and eigenvectors. We have learned eigenvalues and eigenvectors in our previous topics. So let's see some of the properties. Real and complex eigenvalues means if A is a real matrix means a matrix with its entries are real values. Now you can see in example matrix A is a real matrix where 1 0 0 2 are real numbers, so this is real matrix. Similarly matrix B, which is 0 1 minus 1 0, this is also real matrix because its entries are from real numbers. Okay, if matrix is a real matrix, its eigenvalues are real or complex conjugate in pairs. Means if matrix is real, then its eigenvalues may be real or complex, whatever may be the eigenvalues. We have learned in previous topic how to find eigenvalues. Now for given matrix A, eigenvalues are 1 and 2. We all know how to find eigenvalues. Eigenvalues are nothing but roots of characteristic equation, and we know how to find characteristic equation. C A of lambda is determinant of A minus lambda I. We had given matrix A, we find out matrix A minus lambda I, then we find out determinant, then determinant comes in the variable lambda. We say this is a characteristic polynomial. After equating this characteristic polynomial with 0, we get roots of this characteristic polynomial, and these roots are nothing but the eigenvalues of our required matrix. Now for matrix A, eigenvalues are 1 and 2. Similarly for this matrix, we can see that matrix is a real matrix because its entries are real numbers. Still, it is a real matrix, its eigenvalues are not real, its eigenvalues are complex number. Okay, you can check this. Now trace. If A is an n by n square matrix, then trace of A is sum of diagonal elements of A. Sum of diagonal elements of A, which is nothing but sum of roots of characteristic equation. Now if matrix is a square matrix of order n, it will have maximum n roots. So we say first root is lambda 1, second root is lambda 2, and nth root is lambda n. These are just notations. So sum of the all roots of characteristic equation is nothing but lambda 1 plus lambda 2 plus lambda n, and this sum of roots is nothing but sum of diagonal elements. Okay, now here we can say for matrix A, what is trace? For matrix A, trace is sum of diagonal elements. So for matrix A, sum of diagonal elements is 1 plus 2, and this is nothing but sum of roots. Sum of roots, that is sum of eigenvalues. Sum of eigenvalues is 1 plus 2. Yes, so this is also 3. Similarly, we can check this for matrix B. For matrix B, sum of diagonal element, we know diagonal element, this is our diagonal. Sum of diagonal is 0 plus 0 is 0, and sum of eigenvalues is I minus I minus I, this is also 0. So we can check this. So trace is nothing but sum of eigenvalues of matrix A. Now determinant of A is nothing but product of eigenvalues of A. Now we all know how to find determinant of 2 by 2 matrix. If matrix is A B C D, then its determinant is AD minus BC. This determinant and product of eigenvalues of same matrix A both are same. You can check this from above example 1 and 2. Let A be any n by n square matrix, the transpose of matrix A be A transpose. Now we all know what is transpose. If 1 2 3 4 is a matrix A, then its transpose is obtained by reversing rows and column. Means in matrix A, 1 2 is first row, I make row to column. So here I write down this row in a column. So first row becomes first, column. Now this second row 3 4, 3 4 become second column, second row become second column. This is nothing but transpose. Now note that A and A transpose have same eigenvalues. A and A transpose have same eigenvalues. Why? Because determinant of A and determinant of A transpose both are same. From here you can check that determinant of this matrix is 4 1 minus 3 2, that is minus 2. Similarly here 4 1 and 3 2. Similarly here is also minus 2. Okay, so as determinant of A and A transpose are same, determinant of A minus lambda I and determinant of A transpose minus lambda I both are same. So as determinant are same, roots are same, roots are the eigenvalues, so A and A transpose have same eigenvalues. Non-zero eigenvalues. If all eigenvalues are non-zero, then determinant is non-zero. As we all know, determinant is nothing but product of eigenvalues. Determinant is nothing but product of eigenvalues. So if all eigenvalues are non-zero, their product should be non-zero. Okay. But if among all these eigenvalues, if at least one eigenvalue is zero, okay, so obviously determinant is 0. We can say, suppose 1 2 3 are eigenvalues of some 3 by 3 matrix. Suppose 1 2 3 are eigenvalues of some 3 by 3 matrix A. Then you can see that these 1 2 3 are 3 eigenvalues, all are non-zero, their product is 6. Okay, so if you find out determinant of this matrix, this will also be non-zero, in fact it is 6. Okay, but if at least one eigenvalue is 0, suppose 0 1 2 are the eigenvalues of this matrix. Now here I might change the matrix. Now their product is obviously 0, and you can check that determinant of such matrix is obviously 0. We can check determinant and product independently, but in fact both are nothing but same. Now for inverse, if A inverse exists, if and only if 0 is not eigenvalue of A. A inverse exists if and only if 0 is not eigenvalue of A. If eigenvalues of A are lambda 1, lambda 2, lambda n, then eigenvalues of A inverse are 1 upon lambda 1, 1 upon lambda 2, 1 upon lambda n. Suppose 1, 2, 3 are eigenvalues of matrix A, then eigenvalues of A inverse are 1 upon 1 is 1, 1 upon 2, 1 upon 3. These are required eigenvalues of A inverse. Okay. Scalar multiple, let lambda be any eigenvalue of matrix A. Matrix A is of order n, so I choose any eigenvalue, say lambda. Then eigenvalue, if I multiply this matrix A by some scalar multiple k, so I get this matrix k into A. So eigenvalue of such a matrix is also k into lambda. Okay. Power, if A has eigenvalue say lambda I, then A raised to m has eigenvalue lambda I raised to m. If power of matrix happen, power of eigenvalue also happen. Eigenvalues of diagonal, upper triangular or lower triangular matrices are nothing but principal diagonal elements itself. Means what? Suppose this is matrix 1 0 0 2. Okay, what is determinant? Determinant is 1 into 2 is 2. Yes. Now what is determinant? Is nothing but product of eigenvalues. Yes. For determinant, for this diagonal matrix, eigenvalues are nothing but 1 and 2. Their product is again 2. Suppose I take upper triangular matrix 1 2 0 3. Now this matrix also, this is an upper triangular matrix. All entries above the below the diagonal are 0. All entries below the diagonal are 0. This is an upper triangular. We can see here triangle. Okay. So here determinant also 1 into 3. 1 into 3 minus 0 into 2. So it is also 3. And here for upper triangular matrix, eigenvalues are nothing but 1 and 3, which are nothing but elements of diagonal. So again 1 and 3, their product is 3. For lower triangular, suppose 1, 0, 2, 3. What is lower triangular? Triangle becomes in lower part. So what is definition of lower triangular? Lower triangular matrix is a matrix having 0 entries in the above diagonal. Above diagonal there are 0 entries. Now here also determinant is nothing but, you can check 1 into 3 minus 2 into 0 is 3. And eigenvalues, same eigenvalues, you can check this. Eigenvalues of this matrix are nothing but diagonal elements, so 1 and 3. Okay, these are some properties. Now in next part we will see some problems regarding this. Let us see this. Now first one property, real and complex eigenvalues. Same example, let A is a matrix 1 0 0 2, which is a real matrix. Its eigenvalues are 1 comma 2. Let B be an again one real matrix 0 minus 1 1 0. Now you have to find out characteristic polynomial here. Characteristic polynomial, we know how to find characteristic polynomial. Characteristic polynomial is we all know formula of characteristic polynomial, determinant of b minus lambda. Now here matrix is b, so I will take here b. Now you can check this is the characteristic polynomial is lambda square plus 1. Now if I equate this lambda square plus 1 equal to 0, I will get eigenvalues plus or minus I. Same for trace. Let this is a matrix A. Characteristic polynomial is lambda square minus 10 lambda plus 24. Now you have to make practice of such a problems, so you can directly find out trace, eigenvalues and determinant. Now you have to check this by using formula. Characteristic polynomial is determinant of A minus lambda I. You have to do this in your notebook. Determinant of lambda I, you can check, this is nothing but this. And if I equate this polynomial with 0, I will get eigenvalues 4 and 6. Now trace, what is trace? Trace is nothing but sum of diagonal element. Here diagonal elements are 8 and 2, so 8 plus 2 is 10. And sum of the eigenvalues we get eigenvalues 4 and 6, so their sum is also 10. Determinant for same matrix A, determinant is 8 into 2 minus 4 into 2, so this is nothing but 24. Now all we know, this is the same matrix which is described in above. Eigenvalues are 4 and 6, so we all know determinant is nothing but product of eigenvalues. So here product is 6 into 4, which is nothing but 24. Both is same. In this topic just we are checking transpose. 8 minus 4 2 2 is a matrix. A transpose is first row, this is first row become first column, this is second row 2 2 become second column. Eigenvalues of A are 4 6, eigenvalues of A transpose are also 4 6. Check this. How to check? Find out characteristic polynomial for A, find out characteristic polynomial for A transpose, equate these all characteristic polynomial with 0, you will get roots. These roots are nothing but our eigenvalues. Note A and A transpose have same eigenvalues but did not have same eigenvector. If eigenvalues are same, it did not say that matrix has same eigenvector. We will see this problem in our next topic. Non-zero eigenvalues. Now here matrix A, eigenvalues are 4 and 6, both are non-zero, and determinant is 24, which is also non-zero. Yes. Singular matrix. What is singular matrix? Matrix is singular if its determinant is 0. Now this is a singular matrix. Why? Determinant is 8 into 2 minus 4 into 4 is 0. Now let us find out eigenvalues. You find out these eigenvalues for matrix A. Eigenvalues are 10 and 0. Now here one eigenvalue is 0. If one eigenvalue is 0, their product is 0, and we all know determinant of matrix is nothing but product of eigenvalues. Product of eigenvalues. Okay, so A is a singular matrix. A inverse. For matrix A, 8 minus 4 2 2, eigenvalues of 4 6. Now if you find out A inverse, we get A inverse like this. All we know that formula of A inverse is 1 upon determinant of A into adjoint of A. We all know this formula. By using this formula, we find out A inverse. After finding A inverse, we will find out again eigenvalues for this matrix. Now for this matrix, eigenvalues are 1 by 4, 1 by 6, exactly reciprocal of 4 and 6. Scalar multiple for A, 8 minus 4 2 2, eigenvalues are 4 6. If I multiply this matrix A by some scalar multiple k, which is minus 1 by 2, so I will get ka equal to minus 1 by 2 into required matrix A. So final output ka is this matrix. If you find out eigenvalues for this matrix also, you will get minus 2 and minus 3. Now k is minus 1 by 2. So if we multiply minus 1 by 2 to over 4 and 6, our eigenvalues, we will get the same eigenvalues of ka. So what is use? If we have matrix A, if we have eigenvalues of this matrix A, and if there is some relation between A and a given matrix, yes, in a scalar, in power, in inverse, in transpose, so we don't require to find out again eigenvalues for given matrix. This is our use. Similarly for power, if A is our matrix, these are our eigenvalues. If we find out A square, obviously this matrix 8 minus 4 2 2 and 56 minus 40 20 minus 4, both are the different matrix. Eigenvalues of both matrices are different, but which are the eigenvalues? Eigenvalues of A square are 16 and 36. Now you can see that 4 square is 16, 6 square is 36. Now this is example of diagonal matrix. For diagonal matrix, upper part and lower part of the diagonal, principal diagonal is 0. These entries are 0. These entries are 0. Eigenvalues are 1 2 3. This is an upper triangular matrix B. B is an upper triangular matrix. Below diagonal, all entries are 0. This is an upper triangular matrix. You can check eigenvalues are 1 4 6. 1 4 6 we can say directly, because 1 4 6 are our principal diagonal element. For diagonal, for upper triangular, for lower triangular, eigenvalues are nothing but elements of principal diagonal. Similarly for lower triangular, eigenvalues are 1 3 6. Now here wherever I write down check it means what? Try to find out the eigenvalues for given matrix systematically. This is your homework. What does systematically mean? In previous chapter we all know how to find out eigenvalues. So follow the same procedure, okay, for the different problem, and try to solve on paper. As many problem you go through, you will get very nice hand on all this problem. Okay, thank you.